Hello again, welcome back to RadSound FRCR Physics. So I'm going to employ a method of explanation. So we have our source, we have patient, we have image, detector, image formation, optimization, and stuff to one method, every modality. Today we're going to start with the birth of the beam, that's the tube X-ray tube, the origin of the X-ray. So X-ray image begins inside the tube. It is the heart of every diagnostic X-ray unit. It converts electrical energy into X-ray and heat. Okay, let's discuss each component from outside in. Very important. So we got the outer shell, the outer protective layer. Okay, this is the outer layer. What is mostly formed from lining the layers to allow for mechanical support and the protection of leakage radiation. Okay. After that, we have insulating oil between them for insulation, electrical insulation, and also convection of heat outside. So we got the inner layer. Okay, the envelope housing providing muscle is made from ceramic, okay, metallic ceramic or glass, which help in maintain operate or provide a high vacuum that allows electron travel freely without collision from the cathode to the anode. Okay, so let us take a look into the anatomy of the cathode. Cathode is a negative charge. Okay, it's made up of a focusing cap here. So the focusing cap is a good it has a high melting point and low. It's very poor thermionic emitter, and it's also negative in charge. Okay, it is concave in shape, negative in charge. Seats inside or within the focusing cap is what we call filament. So the filament has smaller filament for the most of the common most of the modern diagnostic imaging. Diagnostic X-rays are having dual filament. The smaller filament for small focal spot, which give better geometric resolution. That's it gives better detail of the image, and larger one, which is the larger filament, which is mostly for large focal spot. That large focal spot will help for better heat rating. Okay, so allows a high amount of heat applied without getting having trouble or problems. That's KBP and MAs. So these are the filament, or this is the filament. So what the filament is made of? Filament is made or it's made from tungsten because it has very high melting point temperature and has high atomic number 74. It's also a good thermionic emitter. Another thing to understand is that the focusing cap is not good. It's very poor emitter of electrons. It has poor thermionic emission property or characteristic. So what's happening? How the electron is being formed around the cathode? Okay, the cathode is negative charge. The focusing cap is negative charge. Focusing cap is made from molybdenum, mostly, or nickel, and the filament is made from tungsten. So remember this because of the exam. All right. So now, when the electron, when the voltage, okay, that's low voltage and high current is supplied or applied to the filament, so what's happening? So the filament will become incandescent. This heating gives some outer shell electrons enough kinetic energy to overcome the surface binding forces. That's the outer shell electrons in the tungsten of the filament. Because of the applied high current and low voltage, they will gain energy. Okay, that enough kinetic energy to gain, they will escape from the filament. That is keeping all the electrons from the outer shell of the tungsten as the high current and low voltage applied is called thermionic emission. Thermionic emission is very important to understand this. So because they are becoming clouded or crowded around this area, because the electron become crowded around this area, that process is called space charge cloud. So remember I said the focusing cap is concave in shape. So what's important? That concave shape shapes the electron beam toward the anode. Okay, it shapes them toward the anode so that electron can travel along within the vacuum toward the anode. Okay, so let's say the main space charge cloud become clouded around this area, crowded. So why is it important to understand this? Because as the electron become crowded around this area, they'll produce kind of negative feedback. Negative feedback is very important in medicine, especially in the hormones. So negative feedback will decrease the amount of electrons being escaped from the outer shell of the tungsten because there are much electrons around this area. So we need something. So what are we going to do now? So we will apply high voltage, okay, 2 voltage. That will increase the kinetic energy. Before applying the 2 voltage, we will need something, and we will have to clarify something. The filament current will increase temperature there, and the amount of electron energy. Okay, the tube current, the main tube current, the whole tube current that will apply to the whole tube will actually will allow or determine the flow of the electrons from the cathode to the anode. So the filament current determine the amount of the electron being detached from the outer shell of tungsten, okay, to be coded here. That's the filament current. The tube current will determine the amount of the electrons traveling toward the cathode, from the cathode to the anode, meaning that tube current will determine flow of the electrons in the vacuum toward the anode, while the filament will determine the amount of the electron getting detached, okay, or escaping from the outer shell of the tungsten. After that, we then apply a high voltage across the tube. So cathode is negative, anode is positive. The tube potential accelerates electrons across the vacuum toward the anode. So now we got everything, we got electron, space charge. So we applied the voltage, the tube voltage. So meaning that maximum kinetic energy of each electron can occur equals to the tube voltage applied. Meaning that if we applied 100 kVp tube voltage, each electron in this part has 100 keV, that electrovolts. The unit of energy or electron's energy is electron volt. 100 kVp, if we applied 100 kVp across the tube, each electrons we're going to move with the kinetic energy of 100 keV. So now we understand that the maximum energy, the intensity of the electrons, the cathode to the anode, depends on the kVp. What is the amount of the electrons, okay, produced from the filament depends on the filament current. So current mostly determine the quantity, and the kVp determine the quality. Okay, so now what's happening around the anode? So let's talk. Anode is divided into two different types. Mostly we have stationary anode, we have rotating anode. So for the stationary anode, it has a tungsten embedded inside copper block. So mostly it's not of use today because we are using it for low output procedures such as dental, portable X-ray, because the heat is being concentrated in one place. That will not allow it to be applied because that will lead to problems of the machine. So it is limited for low output procedures. Okay, so now let us talk about rotating anode. Rotating anode is the most commonly used because the anode is rotating. Okay, the anode is rotating, so the heat would be dissipated over a larger area. Number one. Number two, that will allow the electron to be spread across what we call focal track. Focal track is made from tungsten again. So it's made from tungsten. We add rhenium for most of the machine. Rhenium to allow to increase the durability of the anode and also to prevent cracking. Okay, so then we got some areas or the outer part of the anode, which is not the focal track, is being blackened, okay, to increase the heat dissipation. Okay, another part we got something is the body of the anode, which is made from molybdenum. Then we get something here which is called the rotor. The rotor, inside the rotor we got metal bearings. The bearings to allow the rotation smoothly. Okay, so we are using the rotor for lubrication. That inside the rotor we got metallic bearings, mostly with the silver, for as lubricant. So we're not using oil as lubricant. Remember, just because of the exam. So then outside the main vacuum, we got outsider. Okay, so get something called what called stator. The stator are made from most of them from copper. Okay, the rotor also from copper because steam, molybdenum, steam of the anode. The main body or the disc body of the anode sometimes is back to the graphite for additional heat storage capacity. Okay, and to say something about the bearings, the part of it, bearings must withstand very extreme heat at a high speed of rotation. As we mentioned, the rotating anode can rotate up to 3,600, sometimes on the modern machines up to 10,000 revolution per minute RPM. So the bearing inside must tolerate the amount or the extreme amount of heat. Okay, so Mostly, they are, as I mentioned, they're metallic lubricants. Okay, sometimes liquid metal lubricants, but mostly metallic. So, and it is made mostly from silver. So, notice because in exam they may ask you, they may trap you, say liquid is used, or they may say oil is used as lubricant, which is false. It comes in the exam. Let's say something about what you call angle. So, the anode is been placed, it's been angled. This is important physics because that angle will help what you call line focus principle will help to create something. The part of the anode, which is made from tungsten rhenium, the part that is become bombarded by the electrons coming from the cathode is called actual focal support. Okay, so the area bombarded by the X-ray, okay, the beam coming, the electron coming, bombarded area, tungsten rhenium, okay, the focal track is called the actual focus spot. And the after the angulation, we got X-ray coming out through the window. That area from here to here is what we call effective focus spot. The effective focus spot is always smaller than the actual focus spot. Okay, the larger actual focus spot has important advantage, as you remember, because the heat is coming. The electron is coming, heating this area. So if the area is larger, that it will allow large dissipation of the heat, and for longer time that will increase the heat rating or heat loading. Okay, so we got something important also. If to say we get angle, so what is the number of the angle? Mostly the angles between 5 to 20. So you have small angles like 5, we have large angle like 20. So the important and some disadvantages is, using a smaller angle. For instance, we have small angle that will decrease the area here, the effective focus spot. If we use small angle, the effective focus spot is going to be small because the effective focus spot equals actual focus spot multiplied by sine theta, what theta is called the angle we use. So, and sometimes, what will happen? What the apostle call Hale effect or anode Hale effect. Did the anode, did the cathode. The X-ray coming, like it will be, it's more approximate, like it's more toward the anode, toward the cathode. Whereas the X-ray around this area is more toward the anode. So the X-ray toward the cathode is more intense, it has more energy, okay? So that's what you call anode Hale effect. So energy or the energy of the X-rays toward the anode are less, okay? They become more attenuated. So that's the important, because as that happens, we use this process in radiology, especially placing the thicker part of the body toward the cathode because it has more intense. The energy has high intensity, so but they can travel with a less attenuation and allow better imaging. Okay, what happening around the anode? Exactly what's happening. So the anode has also tungsten, and the tungsten out shell, something like out shell, we have inner shell. So at the electron come in, okay, hitting the area, at the heat the atom, so the electron will penetrate. We have outer, we have inner, okay. I'm gonna explain into detail when it comes to X-ray or the photon interaction with the matter, okay. Don't worry for now. So just imagine, okay, we have what the process that the main concept we're going to produce X-ray. So the process of production of the X-ray are two main processes: Bremsstrahlung and terrestrial radiation. What are the basics? The basic is that as the electron coming, heat and bombarding this area of the tungsten, power of 8 will be converted to heat, and power of 8 will be converted to X-ray. So 99% of the kinetic energy or the kBp applied to be converted into heat. So it's very important to have ways to remove the heat from the tube, okay, which are three processes. We're going to just explain a bit of them later. Then the remaining 1%, only 1%, or at least sometimes at most around 1%, that will be converted to X-ray. Out of that 1%, 20% will be through terrestrial radiation, whereas 80% will be Bremsstrahlung. Bremsstrahlung means break radiation. So what are the basics of these two mechanisms? The basic of Bremsstrahlung is that when the electron comes, hits this area, as it goes, it penetrates the out shell, the middle shell, and the inner shell, then toward the nucleus. As the electron travels with energy toward the nucleus, the electromagnetic energy of the nucleus will call it is repelling, okay? Kind of repelling, it will repel to deflect away from the nucleus. So that energy, deflection will release an energy because there will be a decelerate. It's coming with a very high energy, become decelerate, or it becomes decelerated and deflected. That deceleration will release power of its energy. That energy is called X-ray. So this is Bremsstrahlung. Bremsstrahlung is a continuous radiation because the incident electrons have different energies, okay? So it's continuous, whilst the constructed radiation is discrete. So what's the process of production of constructed radiation? And the incident electron comes heat part of the target, or that's the tungsten. It penetrates the outer layer, the middle, the inner. So when it comes to heat the inner, it hits some electrons inside the inner shell, okay, of the atom. That inner shell, that electron inside the inner shell will be displaced, okay, ejected. So there will be a vacant or empty space produced. That empty space will get a replacement where the electron from the outer or the shell before the inner shell will just drop down to fill that vacancy. Dropping of the electron from the outer to inner needs energy. The difference in the energy will be released as characteristic radiation. This is very important in exam. That you will know, you get question from either Bromstrom, and you must have question from the excitator. Characteristic radiation will only be produced if the applied kBp is above the kH. The kH for tungsten is around 69.5, okay, mostly you can say 70. It's divided into two parts. We can have kH alpha, okay, K alpha, K beta. So what's the difference? K alpha mostly we have KLM, okay. The K is the inner, okay. We have L next to the K, we have M next to the next to the L. So if the replacing electrons comes from the L to the K, that we call alpha, okay. It's alpha. So if the electrons comes from the outer M instead of L, so it passes through the L toward the K. So this is called beta. So beta will have more energy because it is far away from the nucleus, or from the nucleus, also from the inner shell. Okay. So the far away, the higher the electrons is more away, the higher the energy that we will need for the replacement, which comes inside to the inner shell to replace the vacancy. And also the nearer the shell to the nucleus, the higher the binding energy. Okay. You have to understand this basis also. So now we have the X-ray. The X-ray will start coming out of the window, okay, to the window. Sometimes some of the part of the window, as in such as a mammogram, but we use beryllium in the window to help with attenuation, okay, by 3 methods mostly. So inside this vacuum, okay, the main method of removing heat is by thermal radiation, okay. Part of the heat will come down, will come inside the vacuum, will be removed by radiation, and the part of the heat produced in the anode body, and the part of the rotor, and the part of the stator, which is the stator, will be removed via conduction, okay. And then another part of it will be called convection, okay, toward the inside the insulating oil. So we have convection. So convection mostly inside insulating oil toward the housing. We have conduction around the anode. We have radiation, thermal radiation within the vacuum. So remember, radiation vacuum inside the metal or ceramic tube. We have envelope, okay. We have conduction around the anode. We have convection inside the oil, okay. So remember these 3 important methods because they're very important. So convection always in the outside, not inside the vacuum. Housing, we have cathode, we have vacuum, bring electrons, acceleration, we have anode to convert kinetic energy into heat and the X-ray. So we have Bremsstrahlung, which is continuous and most important method or process of production of X-ray. So not every component follow every electron, understand every X-ray, okay. Thank you. So see you in the next video, from tube to tissue.